Hello, welcome to the fifth lecture for the chapter 7 of Mathematics, class 11, Binomial Theorem. So, till now, we have seen how binomial expansions are done. So, first we started with the very basic multiplication way to see how you can expand for bracketed terms or expressions like a plus b, the whole square, you can expand it with a plus b and multiplied by a plus b. Okay, so this was a very basic, a way that you can get these expansions. We saw they become tedious after a certain point of time. And also when we try to increase your power of index to say 8 or 12. Okay, so anything larger than that, we face issues when we are trying to expand it. So then we got the entire idea of Pascal's triangle. Okay, so we saw how Pascal's triangle can be used to solve such expansions, to evaluate such expansions. And also we then later on we came to the concept of using combinations. Okay, so like NCR, and then to find the coefficients of the different terms that are there in the expansion. And also we saw that there are some rules which are always followed when they are expanding. So we have already seen those, but there is a method, or there is a proof, okay, that needs to be understood when we are trying to get the binomial expansion. So the proof that we will be dealing with is called binomial theorem for any positive integer n. Okay, so the statement is that for any positive integer n, a plus b raised to n should be equal to nc0 a raised to n plus nc1 a n minus 1 b1 plus nc2 a n minus 2 b raised to 2 plus n cn minus 1 a b n minus 1 plus n cn b n is true. Okay, so this is the statement that we have to prove. So for the proof, okay, so we will start by taking let the given statement be P of n or Pn a plus b the whole raised to n nc0. So write down the statement as we have already put. Okay, so this is the statement, and we are going to consider the statement to be Pn. Okay, so when we take n is equals to 1, okay, so for n is equals to 1, so P1 would be a plus b the whole raised to 1. Okay, so if you write it in the using the normal general way that we are expanding with respect to, or with the help of combinations, so you can write this as, so your n is 1, so 1 c0 a raised to 1, then you have 1 c1. Okay, and now a will decrease, the power of a will decrease by 1, so it becomes 0, and for b it will increase by 1, so it is b1. Okay, so since your n is equals to 2, since your n is equals to 1, since your n is equals to 1, your number of terms would be equal to 2. Okay, so we got two terms. So then you can write this. 1C0 is 1, so this is A. And 1C1 is also 1, so this is B. Okay, so this is your for when n is equals to 1. So therefore, P1 is true. Okay, so now we can see that if this is your Pn is your statement, and if we put in a value for your n, okay, say we have taken 1, so P1 is true. Now let's consider for some positive integer, say k, P k can be written as a plus b. So your n is substituted by k over here, and that would be equal to a c0 a k. Okay, so this follows the first term of the the way we do the expansion with respect to the combinations. Then you have plus k c1 a k minus 1 b. Then you will have k c2 a k minus 2 b2 plus plus k minus 1 a b raised to k minus 1 plus k c k b raised to k. Okay, so this is what we get for any positive integer k. Okay, when the n is substituted by a positive integer k. And let's consider this statement as statement number 1. Okay, now we shall prove that suppose your for k plus 1, okay, that for k plus 1, p of k plus 1 is also true. Okay, so we can say that for some positive integer when we had k, it p of k is true. Okay, so this we have assumed that p of k is true, and hence we had expanded it in this form. Okay, by taking n is equals to k. Now we will try to see that if we change n to k plus 1, then p k plus 1 should also be true. So now you can write a plus b raised to k plus 1. Okay, so raised to k plus 1, you can write it in the form. Okay, so we have to prove that p k plus 1. Okay, so written in this form again, generalized, that it also needs to be true. So we have to say that a plus b k plus 1 has to be equal to k plus 1 0 a k plus 1 plus k plus 1 k1 a k b plus k plus 1 c2 a k minus 1 b2 plus k plus 1 b k plus 1 b k plus 1. Okay, so we have to prove that this is also true. So how we can prove is that you rewrite your a plus b k plus 1, okay, in the form of a plus b multiplied by a plus b raised to k. Okay, so if k plus 1, so you can write it in this form. So now we have already seen the expanded form of a plus b, the whole raised to k. So just rewrite that over here. Okay, so you have k c0 a k minus 1 b plus k c2 a k minus 2 b squared plus then continued up to k c k minus 1 k minus 1 A, B, K minus 1 plus K, C, K, B, K. Okay, so this is what we get. Now what we will do is we will multiply each and every term of the, in the second bracket with the individual terms on the first bracket. Okay, so A will be multiplied with the entire second bracket and then B will be multiplied with the entire second bracket. Okay, so we will write this in the form. And maybe we finish writing it here only. So it's easier for us to follow here. Excuse me for a moment. Okay, so we will first multiply A with the entirety of your second bracket. Okay, so the first term will be K C0. Okay, A is raised to K over here and there is A over here. So this will be A K plus 1. Then you will have K C1. Over here you have A K minus 1 and this is A raised to 1. So your plus 1 and minus 1 gets cancelled. So you have A K B. Then you will have K C2 where you have K minus 2 and then A raised to K minus 2 and A raised to 1 over here. So minus 2 plus 1 is minus 1. So this will be A K minus 1 B squared plus all the way up to the term, the second last term over here. So you have K C K minus 1. This will be 1 1 over here. So this will be A squared B K minus 1. And then over here you will have K C K A B raised to K. Okay, now let's see what you will get. This we have finished all of the terms till the last term by with multiplying with A. Now we will multiply B with the entire second bracket. So the first term would be K C0 A K remains and then B. Then you have plus K C1 A K minus 1 and B raised to 1 and B raised to 1 is there. So this would be B squared. Then you have K C2 A K minus 2 and then you have B squared here and B over here. So this becomes B cubed. Then the second last term becomes K C K minus 1. A, this is K minus 1 and there's plus 1 over here. So plus 1 and minus 1 gets cancelled. You have B K plus you have K C K B K plus 1. Okay, so this is your entire expanded form, okay, where you have also multiplied the first bracket. Okay, now there are a few relations first what we will do is we will group the similar terms. Okay, so group the similar terms. Okay, so the first term and the last term, okay, actually they will not have any similar terms. So those we will write as it is. So first let's write the first term. So that is K C0 A K plus 1. Okay, now the next one is you see that there is A raised to KB. Okay, so there is one term which has A raised to K multiplied by B. You will find that there is another such term over here. Okay, there is KC0 AKB, A raised to KB. Okay, so what we will do is that we will write these two terms together. Okay, so what we get is K C1 plus K C0 A raised to KB. Okay, then the next term that is common will be A raised to K minus 1 B squared. Okay, so there is one term over here like that, and then there is one more term over here. So what you get is K C2 plus k C1 A k minus 1 B square. Okay, so similarly, if you club all of the similar terms together, okay, and then you come to the second last term of, what we had for the second brackets over here. As you see, there is a squared b raised to k minus 1. Okay, so there is one term over here like that, and there will be one more term. Or we can just, go for the second last term that we have. So you have a minus 1 and yeah, so over here you have one term of ab raised to k, and over here you have one more term. Okay, so k c k minus 1 a b k. Okay, so let's write that. You have k c k plus k c k minus 1 multiplied by a b raised to k, and then the last term, as we had said, that we will write as it is. Okay, b k plus 1. Okay, now we know, okay, so this is your, say, second statement. Okay, so this is entire thing is your second statement. Now there are a few relations that we will use. Okay, so we know that k plus 1 c0 is equals to 1. Okay, so which will also be equal to k c0. Okay, so because k c0 is also is equals to 1, so we can substitute that 1 with k plus 1 c0. Okay, so let's denote this as a. Now the next relation that we will use that KCR, okay, KCR plus KCR minus 1 will be equal to K plus 1 CR. Okay, this is your B. And the last one is that KCK is equals to 1, which is also equal to K plus 1 CK plus 1. Okay, so it's in the similar form as, NCN. And this is actually of the form of, NC0. So any NC0, anything, any combination with, when we are trying to take only and zero terms together is going to be written as 1. Okay. So using A, B, and C in 2, we get, okay, so this then actually is P K plus 1, okay, so that is A plus B raised to K plus 1 will be equal to, okay, so over here you have KC0, so in case of KC0, we will put K plus 1 C0, so K plus 1 C0 A K plus 1. So this again comes in the form of NC0 A raised to N, okay. So that is what we wanted to find. We have to prove that this expansion is true. Okay. Similarly, your KC1 plus KC0, okay, over here your R is 1. Okay, in this term, your R becomes 1 if we, correlate it with this relation B. Okay, so then what you write is K plus 1, C, R is 1, so C1, A, K, B. Similarly, the next term, the R is 2 over here. So again, you will write this as, with respect to your relation B, K plus 1, C, R, okay, A, K minus 1, B squared. And then the second last term, okay, we will have K as your R over here. Okay, so K plus 1, C, K, A, B raised to K, And the last term, okay, over here in place of k, c, k, we will write k plus 1, c, k plus 1. Okay, because k, c, k will be 1 and k plus 1, c, k plus 1 can also be written as 1. So we will substitute this 1 with k plus 1, c, k plus 1. Okay, so k plus 1, c, k plus 1. And the last term will be d, k plus 1. Okay, so we have then proved, okay, thus we have proved that pk plus 1 is true when pk is true. Okay, so thus by applying the principle of mathematical induction, Pn is true for every positive integer n. Okay, so no matter what you take as n, say 1 or k plus 1 or say 2, 4, 6, anything. So Pn, okay, so the binomial theorem or the binomial expansion with respect to Pn will always be true. Okay, so this is how we prove the binomial theorem as a whole. Okay, so now we saw that we can prove for any kind of positive integer. Okay, positive integer, we can prove how you can get the binomial expansion and you can get the binomial theorem for it. But suppose your n is not a positive integer, okay, or it is either a negative integer, or it could be any other kind of real number or fraction. Okay, so the problem will arise is that for any index n not being positive. Okay, suppose we are now considering that n is negative. Okay, for any index n and not being positive, n factorial. Okay, so since we always find n c r as n factorial upon r factorial n minus r factorial. Okay, so when n is not positive, okay, when if n is negative, n factorial cannot be defined. Okay, so your n factorial, for n factorial to be existing, your n needs to be positive. But that may not happen. So we need to find an alternate form or alternate way of writing the binomial theorem. Okay, so in that sense, then what we will have to do is that we, in this numerator part, okay, so this n factorial part of NCR or any of the combinations, or when we are trying to find the coefficients of the different terms in the binomial theorem, we have to remove this factorial part. So we can substitute for any n. Okay, so whether it's a negative or a fraction or anything, we need to define a form of writing the binomial expansion where the factorial in the numerator part of the finding the coefficients is not required. Okay, so what then we will do is, suppose you have a plus b raised to n. Okay, so till now, as we have seen, the way we write is n c0 a raised to n plus n c1 a n minus 1 b raised to, sorry, not n, this would be 1. Okay, then plus n c2 a n minus 2 v2 plus any general term in between ncr a n minus r b raised to r, and then the last term would be n c n b raised to n. Okay, so this is what we will get in the general form. Now over here, since we know that nc1 can be written in term of n factorial upon r is your 1, so 1 factorial and n minus 1 factorial. Okay, so now we want to remove the this factorial form of the numerator. So n factorial can, in general terms, n factorial can be written as n into n minus 1 into n minus 2. Okay, all the way up to we reach 1. Okay, and the denominator part we will rewrite as it is. Okay, now over here, if we write n separately and all the other terms, we can club that together in terms of n minus 1 factorial. Like for example, how, if we can write 4 factorial as 4 into 3 into 2 into 1. Okay, so this can also be written as 4 into 3 factorial, because 3 factorial will only consider these 3 terms. So in similar way, we can then write your numerator as n minus n into n minus 1 factorial upon 1 factorial n minus 1 factorial. So what will happen is your n minus 1 factorial and n minus 1 factorial gets cancelled, and what you will be remaining with is n upon 1 factorial. Okay, so this is what we can get. Similarly, when you have nc2, this can be written as n factorial upon 2 factorial upon n minus 2 factorial. Okay, because n minus r. So over here, you can write this in terms of n into n minus 1, and then you can write this as n minus 2 factorial. Okay, and 2 factorial, n minus 2 factorial. So again, this gets cancelled. What you're left with is n minus 1 upon 2 factorial. Okay, so your first coefficient can be written in the form of n by 1 factorial. Then your nc2 can be written as n minus 1 upon 2 factorial. Okay, so when you have, say, n c r, okay, so this we know as n factorial upon r factorial and then n minus r factorial. Okay, so this you can write as, okay, so over here you can write this as n, n minus 1 into all the way. Okay, so you can write all the way up to, say, n minus r plus 1 and n minus r factorial. Okay, and then you can have r factorial n minus r factorial. Okay, so this you can write as n minus 1, n minus r plus 1, and then you will have, this becomes your r factorial. Okay, so this is the way that we can write. Now, if you then write your a plus b raised to, say, n, okay, in the form of the, the coefficients in the form of removing the, the factorial part of your factorial part of the coefficients that we try to find. You can then write is that since nc0 will always be 1, so you can write the first term as your a raised to n. Then you will have n upon 1 factorial. Okay, Then you will have a n minus 1 b plus n minus 1 2 factorial. Then your general term that we'll have like any with coefficient with r. So you can write that as n minus 1 n r minus 1 plus 1 upon r factorial a n minus r b r. Okay. And then you have plus the last term that you have is b raised to n. Okay, so this is how you can find the you can write you can define this as the general form of binomial theorem. Okay, for any integer or for any index n. Okay, so this is how you can write the general form. So over here, as you can see that even if your n is not a positive integer, you can still find the coefficients. Okay, you do not always need the factorial, part of the in the numerator. Okay, because finding the factorial of a negative number is difficult for us. So because it does not, it cannot be defined. So let's see an example. Suppose you are asked to find a plus b to the whole raised to minus 4. Okay, so you can see over here your n is equals to minus 4. Okay, so now we will try to use the general form. So what was the general form? Plus b n is equals to a raised to n plus n upon 1 factorial a n minus 1 b plus n minus 1 upon 2 factorial a n minus 2 b raised to 2 plus n minus 1 all the way up to n minus r plus 1 upon r factorial a n minus r b raised to r plus b raised to n. Okay, so this is what we find. Now there is one thing that we have to observe is that whenever your n is negative, this binomial theorem actually can go all the way up to infinity. Okay, so for example, I'll just see if for this expansion itself. Okay, so a plus b the whole raised to minus 4, you can write this as a minus 4 plus your n is minus 4 upon 1 factorial a minus 4 minus 1 b. Then the next one will be minus 4 minus 1 upon 2 a minus 4 minus 2 b square plus, then the next term would be your minus 4 into n minus 1. Okay, so minus 4 minus 1. Since the factorial is 3, so 3 into 2 over here into 1 if you keep. Okay, so the next one, as you know, that it will go only up to n minus r plus 1. Okay, so if your r is 3, okay, so you can write this as minus 4 minus your r is 3 plus 1. Okay, so this will go up to that. You can generally just write that. Okay, then you have a n minus 3 b cube. Okay, and then the next term will go as minus 4. Then you will have your n minus 1. Okay, then you have 4 factorial in the 22, 1. Okay, so you have n minus 2. And since your r is 4, okay, so this will go only up to r is, over here as minus 4 minus 3. Okay, so this will, if you write in the form of, say, n minus r plus 1. So this is what you get. Okay, because your r is 4 over here. Okay, so then it becomes minus 3. So n minus 3. And then you will have a raised to minus 4 minus 4 b raised to 4. Okay, so now as you can see that there is not, it's not diminishing. Okay, the power goes on increasing. There is no way that, you will be able to reach b raised to minus 4. Okay, because it will keep increasing. Hence, such binomial expansions actually go all the way up to infinity, because the power of b is always going to be your r, and your r is not going to be a negative number. Okay, so we have to remember that r will always be a natural number. So therefore, whenever n is negative, the expansion can go up to infinity. Okay, so the terms of the expansion. Okay, I'll just change this part. Okay, so the terms of expansion can go up to infinity. Okay, so for now, let's just, you can be given that find up to 5 terms or find up to 4 terms. So suppose over here, we try to find up to the 4 terms. Okay, so up to 4 terms, what will be the, the expansion as a raised to minus 4. So this is minus 4 over here. So the sign over here will change with minus 4, a raised to minus 5b. Okay, over here you have 2 and you can cancel. So this is minus 2 multiplied by minus 5. Okay, so that becomes plus 10 a raised to minus 6b squared. Okay, now actually if you see, even in these expansions, your powers of a and b, okay, if you add them up, they'll still remain n. So minus 5 plus 1, this will be minus 4, minus 6 plus 2 will be your minus 4. Okay, so that rule is still being followed. Okay, so the next one, before we write the sign, let's see what the coefficient comes up to be. Okay, so this is your 2 again. You can write, you can cancel. This is minus 2 over here. Okay, and over here, this becomes actually minus 4 minus 2. Okay, minus 3 plus 1 will become minus 2. So minus 4 minus 2 is actually minus 6. So this you can cancel and write minus 2 over here. Okay, so over here again you get minus 2 multiplied by minus 2. So that is 4. Okay, positive 4. Positive 4 multiplied by minus 5 will become minus 20. And this will be a. So this is supposed to be minus 4 minus 3. So this is minus 7b cube. And then the last term, as we are only seeing up to the, say 5th term, or if you are asked only till 4th term, then only the first 4 terms of the expansion can be written. Now the 5th term, let's see, since we have already expanded, we'll see what it comes down to. Okay, so this is minus 7, this is minus 6, this is minus 5. Okay, so you can cancel 4 and 4 over here. So there's just one negative sign here. Okay, so 3, 2, okay, this also gets cancelled. So this will again be minus 1. Over here, what you are remaining is with minus 1. Okay, so now you can see minus into minus 5. So this would be 7 into 5. So this will be plus 35. Okay, and this will become minus 8b4. Okay, so this way you can carry on. Okay, this will go all the way up to your infinity. Okay, so this is how you can find the expansion of any kind of term where you have a negative power of index. Okay, so mostly this chapter won't deal with a lot, but you can be asked, such kind of expansion, or actually these will come in handy when we go into, other kind of sequences or series, or, when we use such kind of expansions in physics. Okay, so that time we do sometimes get, power, or suppose if you are, given in the terms of a plus b raised to 4. Okay, either you can expand this separately and then find the answer, or you can totally, you can convert it into the negative power of index, and then, you can do the binomial expansion too. So suppose you are asked to solve for 1 minus x raised to minus 2. Okay, so suppose this is what you are getting. So let's first see what we would get if we have 1. Okay, or we'll see 1 plus x over here. Okay, so that would be easier to understand. Okay, so first let's see what we would get if we have 1 plus x raised to n. Okay, let's expand this and see. So remembering what we have done, in the general form, a plus b raised to n can be written as a raised to n plus n upon 1 factorial a n minus 1 b plus n minus 1 upon 2 factorial, and you have a n minus 2 b2. Okay, NCR is, sorry, not NCR, we'll write this as n minus 1 all the way up to n minus r plus 1 upon r factorial multiplied by a n minus r b r. Okay, and then plus NCN b raised to n. Okay, sorry, not n raised to n, this will be 1 itself. Okay, so plus b raised to n. So similarly, we will try to find over here what would this be. So first we'll have 1, okay, because a raised to n. Then you will have n. N upon 1 factorial will remain a. So you will have a. Okay, so over here you will have your a is 1. Okay, sorry, so I don't have a over here. So your a is 1. So what you're remaining with is x. Okay, nx. Then plus you will have now n minus 1. Okay, 2 factorial over here x squared. Then plus n minus 1. Okay, n minus 2 upon 3 factorial x cube. Then all the way up to your, any general term, n minus 1, all the way up to n minus r plus 1 upon r factorial. This is a, so a is your 1, so we will not write a over here. Sorry, r plus 1. So you have x raised to r. Okay, and this will go on. So now for n is equals to minus 1. Okay, suppose we are finding this now. So 1 plus x raised to minus 1. Okay, let's do it for 1 plus x raised to minus 1 first. Okay, so what this will become is 1 plus, say, n becomes your minus 1. So 1 minus 1 into x. Then this will be minus 1 minus 1 minus 1 upon 2 factorial is 2, x squared. Then you have plus minus 1. Let's, just write up to 4 terms. Okay, so, we do not go all the way. Okay, so let's say up to 4 or 5 terms we will try to write. Minus 1, minus 1. Okay, so this will be your 3 factorial. So this will go up to your n minus r plus 1. So this should be going to n minus, since r is 3. So minus 3 plus 1. So the minus 2. So minus 1, minus 2. We have x cube. Then this will be, the fourth term will be minus 1, minus 1, minus 1, minus 1, minus 2. Since we are going up to 4, we will stop at minus 1, minus 3. Okay, and 4 factorial 2 into 1, and this will be x raised to 4. Okay, and so on. Let's keep it up to 4 terms. So what we get now is 1 minus x. Okay, and over here you have minus 2 over here, so this will get cancelled. Minus 1 becomes plus 1, so you have x squared. Plus over here you get this as minus 3, this as minus 2. So 3, 3, 2, 2 gets cancelled. You have 3 negative 1, so that would be again minus 1. Okay, so see how this sign is also changing over here. This is minus x cube. Then the next one we will have minus 4. So all of these actually get cancelled by your, the other factors, and what you are remaining with is minus 1, and minus 1. So there are 4 minus 1. So this would be a positive. So this is x4. Okay, so similarly, even, just with your logic, you can see that the next term would actually become minus x5. Okay, and so on. Since we are having n as, a negative number, it will go up to your infinity. Okay, so now let's solve for 1 plus x raised to minus 2. Okay, so 1 plus x raised to minus 2. Okay, so now since we remember 1 plus x raised to n would be 1 plus nx plus n minus 1 by 2 factorial x squared plus n minus 1, n minus 2, 3 factorial x cube. Okay, and we will we will write up to the fifth term. So this is 1, 2, 3, 4. This is the fifth term will go up to n minus 3. Okay, n minus 1, n minus 2, n minus 3, 4 factorial x raised to 4. Okay, so on. Now we'll take n is equals to minus 2. So 1 plus x raised to minus 2 would be 1 plus minus 2 into x plus minus 2. This is minus 2 minus 1 upon 2 factorial. Okay, so that actually you can write it just as 2. Then you have plus. Again, you have minus 2, minus 2 minus 1, minus 2 minus 2. This is 3 into 2 into 1. Sorry, over your x squared will come. Now over your x cube. Okay, and then again, you have minus 2, minus 2, minus 2, minus 1, minus 2, minus 2, minus, sorry, this one again be minus 2, minus 3. Okay, so 4 into 3 into 2 into 1 and x raised to 4 and plus 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 all the rest of the terms that you have. Okay, so let's write up to the fifth term. So this is 1 minus 2x. Okay, over here you can cancel out. So you have minus 1 into minus 3 over here. So this becomes plus 3x squared. Then over here you can cancel 2 over here, and this is your minus 3. So 3 also gets cancelled. You only minus 1. So minus 1 is 1, but 1 is then multiplied by minus 4. So this will be minus 4x cube. So you can see there's a pattern that is being called that every alternate term will have a negative sign. Okay. And then similarly, the next one would be, there is minus 3 here, minus 4 here, and this is minus 5. So again, 2 gets cancelled, 3 gets cancelled, 4 gets cancelled. So you have minus 1, 1. 1 into minus 1 is again minus 1. Minus 1 into minus 5 will be 5. So again, you will have plus 5x raised to 4. Okay, so on your expansion will go on. Okay, so you can see how the the way the expansion will go. Again, there is a pattern being followed. Okay, so suppose we now change the sign in between. Okay, so over here now we will directly write. Okay, so we will have 1 minus x raised to minus 2. Okay, so the first term will be 1, then plus, or now with negative, whenever we have negative in the binomial expansion itself, or the term already has a negative sign, so every alternate term will have a negative sign already. Okay, so you keep the negative sign. Now you put in your next term will be nx. Okay, so n is minus 2 and you have x. Then you put plus again. Then you have n minus 1. Okay, since now you will have a 2 factorial. So 2. So that is n minus 2 minus 2 minus 1 x squared. Then plus you will have then minus 2 minus 2 minus 1 minus 2 minus 2. And this will be 3 factorial. So 3 into 2 into 1. And you will have x cubed. Okay, so again, as sorry, I made a mistake with the sign again. Yes, so this will be minus. Okay, because we have a minus between a and b over here. Okay, so then the next one will be plus, and then the next term. Okay, so now we are going up to the fifth term only. So again, you have minus 2 minus 2 minus 1 minus 2 minus 2. This will go up to minus 3 only because r will be 4. So 4 into 3 into 2 into 1. And this is x raised to 4. And then plus so on. Okay, so now we will get the simplified. So this will be 1. Now this will be plus. And you will have 2x. Okay, and over here you have 2 and you have so this will be your minus 1. So minus 1 into minus 3. So this will be plus 3. Okay, so this will be your plus 3 any which way, and there's a plus here. So this is plus 3x squared. Then you get this. Okay, so 2, 2, this is minus 1. This is minus 3. So this will be minus 1. So minus 1 into minus 1 is 1. 1 into minus 4 is minus 4. Minus 4 and minus 4 over here. So over here, this will be 4x cube. And similarly over here, your 2 will get cancelled. Minus 1, minus 1, minus 1. And you have minus 5 here. So you have 4 negative terms. So all of them multiplied together will give you a positive only. So this is 5. So this will be plus 5x raised to 4. Now over here you can see when you have the negative sign between 1 minus x, with respect to 1 minus x, the whole raised to minus 2, all the signs of all the terms, okay, in between all the terms is positive. Okay, so it's opposite to what we had when we had 1 plus x, the whole raised to minus 2. Okay, so now you can see that it is easy, because we have already deduced this general form, okay, this general form of writing, this general form of binomial theorem. So it is easy for us to calculate for any kind of integer. Okay, so whether it's a positive integer or a negative integer. So we will stop here for today. There are a few special cases and observations that are seen in binomial theorem, the proof that we did. Okay, so we will move on with that, and also we will solve examples in the next classes. So thank you for attending.